My name is Avi Paulson. I'm an assistant professor of mathematics at Virginia Tech. Welcome to part 2 of a series of videos where we'll explore Fourier series with the lens of linear algebra. In part 1, we reviewed the concepts of inner products and norms from linear algebra. In this part 2, we're going to look at orthogonality using the concept of inner products. In part 3, we'll hit the highlight Fourier series as best approximations, and finally, in part 4, we'll look at the Dirichlet kernel that will help us understand the convergence of Fourier series. Now in this part 2, where we look at orthogonality, the objective will be to be able to calculate best approximations using orthogonal projections. But enough of the setup, let's do some math. Orthogonality. You're used to talking about that in the plane, in 3D, where you have vectors. But what does it mean for two functions to be perpendicular or orthogonal? What does it mean to have a 90-degree angle? Okay. In our setup, V will be a vector space with scalars, either the real numbers or complex numbers. And from now on, our vector space will always be endowed with an inner product and an associated norm, as we saw in part 1 of this series. Now, we say that two vectors are orthogonal simply if the inner product is 0. This is an analogy with the dot product that you're used to in Euclidean space. Now, in Euclidean space, you have all sorts of theorems if vectors are orthogonal. For example, the Pythagorean theorem. Do we have something similar in any kind of a vector space? Well, yes. If the Pythagorean theorem says that if you have two vectors that are orthogonal, then indeed the magnitude of the sum squared equals the sum of the magnitudes squared. And the proof uses the properties and definitions of norms and inner products. That is, the best way to prove it is to say, well, let's start with the sum squared. Well, we can expand that as an inner product, distribute all the terms, and then because the two vectors are orthogonal, the mixed inner products disappear, and you're just left with the sum of the norms, each squared. Orthonormal, what does that mean? Well, we say first that a set of vectors is orthogonal if the inner products of any two of the vectors is 0, that is, any two different vectors. Okay? In this definition, I decided to omit all 0 vectors. One could, of course, say that the 0 vectors are orthogonal to any other vector, in fact, orthogonal to itself, but that creates some annoyances, so let's just throw out any 0 vectors and say that our vectors are non-zero. Now, if in addition that all the inner products of any two different vectors are 0, if in addition you have that the magnitude of each of the vectors you're working with is 1, well, then we say that these normals are normal. That is, they have been scaled to be length 1. And combined with the orthogonality and the fact that the vectors are normal, we say that the set of vectors is orthonormal if these two conditions are fulfilled. Now, let's define a projection. So I'm going to start with a vector here that has magnitude 1, so it is normal. But it's a single vector, so I'm not going to really talk about anything being orthogonal quite yet. Now, I define the projection of a vector in the direction of the normal vector that I start with to be the inner product of the vector paired with the normal one times the normal vector. Now, the motivation of this comes from what you're used to in the plane. We have a little example here. So here I have a picture of a vector 0, 2 along the y-axis, and then I have a normal vector here, 1 over root 2 in the x-coordinate, 1 over root 2 in the y-coordinate, and I'm going to calculate the projection of f onto phi. Okay, how would I do that? Well, according to this definition, I look at the inner product, which in the Euclidean space is the regular dot product. I'm just going to write it out. Inner product here of the vector 0, 2 with the vector 1 over root 2, 1 over root 2. And this whole thing times the vector 1 over root 2, 1 over root 2. Okay? Well, if we do this dot product, let's see what happens. The inner product gives us 0 times 1 over root 2. That's just going to be a 0, plus 2 times 1 over root 2, which we can simplify to being just root 2. So we have 0 plus root 2. The inner product here is root 2. So we can summarize that here. Now, this then multiplies the normal vector that we started with. So out comes just the vector 1, 1. And on this picture, it is the green arrow that points at a 45-degree angle, and it is longer than the original. So some of the things that we see here is that, first of all, it's in the direction of the, or I should say it's parallel to the normal vector that you started with. And you can sort of get the length by drawing the dashed blue line here, which is perpendicular to the line through the original normal vector. Okay, so it's an orthogonal projection. Okay, so this is how you project one vector onto a normal vector. Now, projecting onto a single normal vector is one thing, but what if you want to project onto a whole set of orthonormal vectors? Well, we reviewed some concepts from linear algebra, but you may not necessarily recall subspaces, span, and so forth. So if you don't remember that, you should maybe pause the video now and look up what a subspace and a span is. Now, what we want to do is that we want to project a vector onto a subspace. Now, that you're able to do by doing the analog of what we did for the projection onto a single normal vector, except when you project onto a subspace that has a basis of orthonormal vectors, phi 1 through phi n, you do the projection onto each individually and then add up the result to get the total projection. Let's do an example here from 3D. Now, in this coordinate plane, we are given two basis vectors for the xy plane, phi 1 and phi 2. And then we have this vector f, the blue arrow here sticking into the first octant. And we want to project it into the xy plane. Now, graphically, you may see that we just drop it perpendicularly down into the xy plane, like so. But let's see what comes out if we perform these calculations. Now, we start with our vector f, which has coordinates 1, 1, 1. We dot it with the first of the basis vectors, phi 1 say, which is 1, 0, 0. And we apply this dot product to the first basis vector, 1, 0, 0. That's the first projection, and now we just project on the second one. So we take the vector again, take a dot product of it with the second basis vector, which is 0, 1, 0, times the basis vector. Now, it's quick work to see that these two dot products that we have here both equate to 1. And so we get 1 times the first basis vector plus 1 times the second one. In total, that adds up to the vector 1, 1, 0, which is exactly what you would have expected by perpendicularly dropping the original blue vector into the xy plane. So that shows an example of how to do projections onto a subspace in the case of vectors in Euclidean space. But remember, our goal is to eventually move to spaces of functions. Now, we've talked about projections onto subspaces. And in order to do that, we needed an orthonormal basis. That is, an orthonormal set of vectors for that subspace. What if you don't have an orthonormal set? What if you only have a linearly independent set, or just a basis? Maybe they aren't orthonormal. What do? Answer is the Gram-Schmidt process from linear algebra. You basically start with your first vector, you scale it so you get the normal part right, then you move to the next vector, and you look at the part of it that is orthogonal to what you already had. Scale that, and keep on going that way until, for the last vector, you take something that is orthogonal to everything that you've had before and scale it appropriately. So that's how you can create an orthonormal basis, certainly in the Euclidean setting. Now, what about this orthogonality property? That is, when we were talking about the projections in Euclidean space, we motivated them by drawing orthogonal lines, doing these orthogonal kind of projections. In the definition of our projection onto a subspace, say, there was nothing obviously inherently orthogonal to anything else. So are projections orthogonal? Well, yes, they are, and we can go through these calculations. If you look at the vector f minus the projection, and instead of looking at the inner product with anything in the subspace that you're looking at, let's just look at how it inner products with a basis vector from your orthonormal basis. Well, write out what the orthogonal projection is. It is the sum that appears here. Then expand. Take the inner products. Distribute the inner products. See all these inner products between basis elements. Remember, you started with an orthonormal basis. All these inner products disappear. They're zero because you have an orthonormal basis, unless you're looking at the inner product between a basis vector and itself. In that case, because you have an orthonormal, emphasis on normal basis, then the inner product is just 1 because you just get the magnitude of the basis vector squared. So out comes the vector f you started with, inner product with the basis vector minus the same, which just goes to 0. Now I claim that this then shows that no matter what kind of a vector you take from your subspace, you will see that the inner product is 0 by just doing this successively on all of the basis vectors, because you can take any vector in the subspace and write as a linear combination of vectors from your from the basis. Now, best approximations. Now, projections are nice because they form best approximations. So let's say you start with some vector. And then you have some subspace. And note this vector that you start with need not be an element of the subspace that is of interest. So how would you best approximate that vector with an element from the subspace? Well, the element that best approximates is the projection. And this is a theorem. So let's look at the proof. Well, let's start with just any vector from your subspace. Let's write it as a linear combination of the orthonormal basis vectors. Okay, so the betas are our coefficients here. Okay, now for convenience, this is not clear why you would need this at this point, but let's for convenience define alpha sub I to be the inner product of the vector f with the ith basis vector. Okay, now what we want to look at is the magnitude of the difference between f and the approximation w. And we haven't chosen the w yet. Now, because from part 1 we're experts on the properties and definitions of norms and inner products, we know that we should use the square of the norm, because that allows us to utilize and connect it to the inner product. So we write out the inner product and then start expanding. That is, you get f inner product with f, that gives the f squared, and then you pair it with the w and so forth. And all I've done is I've expanded this inner product, and for w, I've written in its expansion in the orthonormal basis vectors. Okay. Now, next step is to expand these inner products. Now, we're conjugate linear in the second coordinate, and if you start expanding, you see that you get inner products between the vector f and standard basis vectors. And remember, for notational convenience, we call the inner product between f and the standard basis vector phi I we called it alpha I. So all I've done is that it looks very slick, but I just put in the alpha i's in the appropriate locations. Okay? Now, the sums you're looking at there, so it is not clear to where to go if you just look at the sums sort of individually, but as a whole, then it kind of looks like an expansion. Okay? An expansion of sort of alpha plus beta I squared, so some sort of expansion of that type, because you have the bi squareds, you have the two mixed terms. All you're missing is the alpha I squared term, the norm of alpha I squared. Okay? And so when you recognize that, you can introduce it and subtract the same term. And then you gather and set up things just based on that intuition. Okay? And so note at this point that the vector f was given. The vectors alpha I, they are also fixed. They are how the vector f, the given vector f, interacts with your basis vectors. The betas are the only thing you get to choose. Those are the coefficients from the vector w that you get to choose. So how should you choose them to get the smallest possible difference? Well, it's pretty clear from looking at this. You should choose the beta i's to equal alpha i's. So in fact, you have an inequality. When you choose the beta i's equal to alpha i's, you get just the norm of f squared minus that sum of the alpha i's squared. Okay? With equality only when the beta i's are selected as the alpha i's. But note that that choice forces you to select the beta i's as the inner product between f and the ith basis vector, which is exactly gives you the definition of the projection. So w has to be the projection of f onto your subspace. Aha! So that completes the theorem. You have proven that the projection is the best approximation. Now, in Euclidean space, you're used to having finite bases, but when you move into spaces of functions, then most of the time you're dealing with infinite dimensional sets. So you could think, well, if I'm projecting onto a subspace of functions where you have an infinite subspace, maybe I should just keep on, picking more and more basis functions to get closer and closer to anything in there. Okay? Now, what if you were to do that? Now, let's first note that the previous theorem has as a corollary that if you take the coefficients of the projections, the f paired with the phi i's, and square them, then the sum of these coefficients squared is no more than the function f squared. And that just comes straight out of the inequalities that we had in the proof. Now, what if you were to go up to infinity? Well, that recreates a famous inequality in analysis that is quite useful that is called the Bessel inequality. And when you have the Bessel inequality, if you know something about the convergence of sums, of series, that you know that it is impossible to add up things, an infinite sequence of things, unless the elements in the sequence go to 0. So that recovers another famous result from analysis called Riemann's lemma that says that when you are pairing a function with a basis element and you go infinitely far down along your list of basis elements, then you have to go towards 0. So that gives some ideas of how you go towards infinity. But now, to summarize what we've been doing, we're talking about orthogonality here in part 2, and our objective was to be able to calculate best approximations using orthogonal projections. And the highlight of what we saw was that the projection onto a subspace gives the best approximation. And then we did a couple of examples where we calculated said projections. Now, equipped with the concept of best approximation, we're headed for part 3, Fourier series, the highlight of the series, where we will view Fourier series as best approximations, that is viewed through the lens of linear algebra. Coming up next.